Hi and welcome to Module 5.9. So we have seen how to implement a filter. Now it's time to see how to design a filter in a way that is very engineering oriented. So here in the second installment of filter design, we will take simple filter prototypes that are so simple that just by changing the positions of their poles and zeros in the complex plane, we can change their behavior in a very intuitive manner. These filters that we will see in this module are a little bit like the Swiss Army knife of the signal processing engineer. And you will see an array of very simple but yet very powerful structures that you should remember for your future signal processing projects. Welcome to Module 5.9 of Digital Signal Processing. This is part 2 of our 3-part series on filter design, and in this module we will talk about intuitive filter design based on the properties of the transfer function. You remember that in the first module devoted to filter design, we designed filter based on an ideal prototype. In this module, we will look at the general problem of filter design, and then we will tackle a series of intuitive IIR designs that are based on the locations of poles and zeros in the complex plane. Many signal processing problems can be solved using very simple filters, so it is important to master the simple structures. We have already seen some examples, such as the leaky integrator and the moving average. In general, when we use low-order sections, we can intuitively understand what goes on in the frequency domain just by looking at the pole zero plot. Consider the problem of designing a simple low-pass. We want the low frequencies to go through, we want to remove the high frequencies, and we can use such a filter in audio problems, in communication engineering, or in control systems. We have seen a very simple example of a low pass, which is the leaky integrator. But now we know the transfer function by heart, this one, and we also know the CCDE. We can plot the poles and the zeros of the leaky integrator on the complex plane, and we find that there's only one pole in lambda, so when lambda is less than 1, the filter is stable. In the frequency domain, the frequency response looks like this, and it gets more and more concentrated around the origin as lambda gets closer to 1. The block diagram for the filter is a simple feedback loop with a unit delay that pipes back the output into the input. Now that we know how to design a leaky integrator, we can adapt the design to obtain a resonator. A resonator is a narrow bandpass filter that is often used to detect the presence of a sinusoid of a given frequency. A classic circuit that uses resonators is a detector for DTMF signals. DTMF stands for dual tone multi-frequency signaling, and it is the way an analog telephones communicates to the central office the dial number. Whenever you press a number on the dial pad of telephone, you generate 2 frequencies that will have to be decoded at the central office to determine which key you have pressed. The idea is to obtain a resonator by shifting the passband of the leaky integrator. Remember, the leaky integrator has a pole in lambda here, and the idea is to move the pole radially around the circle of radius lambda to shift the passband at the frequency that we're interested in selecting. Since we want a real filter, we also have to create a complex conjugate pole at an angle that is minus omega 0. The transfer function of this system is simply h of z equal to some gain factor that we will determine later, divided by 2 first-order terms that correspond to the 2 poles in the complex plane. As for the poles, we can conveniently express them as lambda times e to the j omega 0, where omega 0 is the frequency we want to select. In the time domain, the output is the gain times the input minus a1 y of n minus 1 minus a2 y of n minus 2. So we have 2 output samples that are delayed and fed back into the input. The coefficients a1 and a2 we can determine if we work out the product of these first order terms. Let's work a little bit on the transfer function. We start in factor form, and then we can work out the product to obtain this canonical form in which we can find the coefficients that we will have to use in the CCDE. So a1 is 2 times lambda cosine of omega 0, whereas a2 is minus magnitude of lambda square.
In the frequency domain, the resonator indeed behaves as we expected. We have now two peaks in the frequency response that are centered on the frequency of interest omega 0, which in this example is equal to pi over 3. The phase is again nonlinear, as we expect from a leaky integrator, albeit modified. The problem with this resonator is that it's not very selective because the pass bands are quite spread out. We can improve the selectivity of the resonator by choosing a value for lambda that is closer to 1. And indeed, if we choose lambda equal to 0.99 for the same frequency of omega 0 equal to pi over 3, we obtain two peaks that are much more narrow and centered around the frequency of interest. As for the filter structure, this time we have two delays. It's a simple feedback loop once again, but a second-ordered feedback loop in which the input is first delayed by the first delay and then piped back via the factor 2 lambda cosine of omega 0, and then delayed again and piped back via the factor magnitude of lambda squared. Let's look now at a DC removal filter. DC stands for direct current, and when we say that the signal is DC balanced, we mean that the signal has zero sum, or zero mean, if you will. The reason why we want signals to be DC balanced is because a DC offset carries no information, but throws the circuits off by wasting current in the loop. A DC balanced signal will have a Fourier transform which is equal to 0 for omega equal to 0. Remember, if you think of the definition of the Fourier transform, you have that. And for omega equal to 0, this is simply the sum of the signal samples. So in order to remove the DC bias from a non-zero centered signal, we need to kill the frequency component at omega equal to 0. The way to do that is rather straightforward. We simply place a 0 at z equal to 1, which is the point in the complex plane that corresponds to a frequency of omega equal to 0. Transfer function is very easy. It's 1 minus z to the minus 1, and the CCDE is equally easy. The output is computed as the difference of two subsequent samples, so x of n minus x of n minus 1. If we plot the frequency response, this is the characteristic we obtain. Indeed, the Fourier transform will be set to 0 in 0. However, this is definitely not an acceptable characteristic because it introduces a very big attenuation over almost the entirety of the frequency support. What we want really is a notch, which is to say we want to put the Fourier transform at 0 in 0 and leave the rest of the spectrum untouched. So we need to somehow improve on the design, and if we remember the circumstant method, we know that we can push up the Z-transform by putting a pole in the vicinity of the 0. So we try and do that, and we combine therefore the effect of a 0 in 1 with the effect of a pole close to 1 and inside the unit circle for obvious reasons of stability. So this is really the combination of a notch in 0, which is given by the numerator here, and of a leaky integrator at the denominator. In the time domain, we have that the output is now lambda times the output at n minus 1 plus x of n minus x of n minus 1. If we plot the modified notch, we obtain a characteristic that varies with different values of lambda. And as lambda grows closer to 1, the notch becomes more narrow. And so here, for instance, the example is for lambda equal to 0.98, and we have achieved a very selective DC removal. The filter structure is very simple. We will exploit the direct form 2 that we have seen in the previous module and share the delay between the feed forward and the feedback part of the filter. Finally, let's consider the hum removal filter. The hum removal is to the DC notch what the resonator was to the leaky integrator. In other words, the hum removal is a DC notch whose stop band we shift in order to be able to eliminate a specific frequency. A classic use case for the hum removal is in music. Amplifiers and electric guitars tend to pick up the hum generated by the AC current in the mains. that frequency is 50 Hz in Europe and 60 Hz in North America. 50 or 60 Hz are well within the hearing range, so not only is the hum audible, but it is also particularly irritating. So we need a filter to remove the hum, and we need to make sure that we can tune this filter according to whether we're playing in Europe or in North America. The strategy is going to be exactly the same as the one we used to derive the resonator. We take a DC notch that has a 0 in 1 and a pole next to it, and we move both the pole and the 0 along a circle of radius lambda and 1 respectively. Of course, in order to have a real system, we have to introduce a complex conjugate pole and a complex conjugate 0 at an angle that is minus omega 0. When we do that, we obtain a second order transfer function with a second order numerator and a second order denominator. If we plot the frequency response, we get the characteristic that we're looking for, and we're placing the notches now at a frequency of interest omega 0. The structure is a standard direct form 2 implementation where we have shared the delays between the feed forward and the feedback part of the filter, and the coefficients can be worked out by carrying out the products between the first order terms in the transfer function.